Hi everyone, and welcome to my second session, last session for today. It's quite late, I noticed, at least at my place, and I'm gonna pitch a new or emerging research community that tries to bring together ideas from social choice theory and make them applicable to AI safety and also AI ethics. And it's basically coming out of a workshop we had in December in Berkeley with a number of kind of high-ranking people from AI safety and also experts in social choice. And I want to tell you what that even is, social choice. I give a very short crash course so that you know what it is and whether it applies to your work as well. Okay, so overall, we have a website. I can also put a link here into the chat. And we also have another workshop in October, right before a major AI conference. So you can still register for that. And we also have a mailing list, and we have position paper and so on. And the links are all in the chat. So just to locate it in my personal overall vision, where it makes sense to think of social choice when designing AI systems or AI agents. Those who visited my other session have seen this slide before, where we were focusing on this left-hand part, and now we will be focusing on this part, where it's about the question: who should actually decide what an AI system should do? And how should they decide this? Most powerful AI systems affect not just a single person, but many or several stakeholders. And one might argue that they all should have some say on what the agent does, what the system does, how it makes decisions, and so on. And this immediately makes clear this is a collective choice. And social choice theory is the branch of science that deals with that for hundreds of years. So it probably has something to say about that. Let's start with some motivating example what social choice theory is all about. Let's forget about AI for now. Let's assume we have a parent here, and in the morning they want to plan how to spend the afternoon with their kids. Three kids, and four options exist. They might want to go to the theater. This is Kermit. They might want to go to the ice cream parlor or to the swimming pool, or they might visit grandpa. And let's assume the preferences as known to the parent of these kids are as follows. This child wants to go to the theater most, and his second choice would be the ice cream parlor, and least preference would be a swimming pool. And similarly ranked options for the other kids, like the daughter here wants to go to the swimming pool and doesn't want to go to the ice cream parlor. So if we have preferences like that and we don't know anything else, like the parent doesn't know how strong these preferences are and cannot also elicit these preferences from that kids. If she asked, for example, if she were to ask, how strongly do we prefer the theater over the ice cream parlor? Well, the child would not really be able to answer that. It might actually also exaggerate their preferences. So the only information that we have is rankings. So what could we do? We could get the idea that we compare pairs of options and see which pairs of options would beat which other pairs if they were compared one by one in a majority vote. And then we come up with a diagram such as this one here, where it seems like there's no option that would beat all the other options in a pairwise comparison. So it might seem that all the four options are equally okay, but then you notice that two of the options beat two others, whereas the other two beat only one. So at least taking one of those that beat two, namely ice cream parlor or visiting grandpa, might seem okay at this point. So the parent decides, okay, we'll visit grandpa. Maybe grandpa is happy if we visit him. Now, at lunchtime, let's assume they learn that the theater is closed. So the theater is no longer an option. Now, one might think, okay, we didn't choose theater anyway. So why should this matter? But if we cross out the theater here in all the three rankings, then it turns out the ice cream parlor now beats the remaining two other options. So it would be really hard to defend now to actually not go to the ice cream parlor, because it's kind of a clear pairwise winner. Such a winner is called a Condorcet winner in social choice theory. And most theorists seem to think that a Condorcet winner should win. So it seems like in this situation, the deletion of this one option, which did not win beforehand, still brings about a change in the choice. You could also argue, because this is a possibility, grandpa should not have been the choice in this diagram in the first place. But the problem is, if you delete other options, it might well lead to grandpa being the only choice left, at least in some situations. So this is a typical question here for social choice theory, is about consistency of collective choice. In this case, it's an individual choice, but it's made on collective preferences. So it's something like a collective choice, or at least it's something like a preference aggregation. The consistency properties of choice mechanisms when you make certain changes to rankings or to the set of options and so on. You might also ask whether this being the choice here, whether that implies anything about utility, about the concept of utility, whatever that is. So these are typical questions asked by social choice theory. Now, there is already some relationship between AI and social choice theory and collective decision making, but not in the direction that I want to look at, but in the other direction. Namely, many researchers have had the idea that AI might help in making collective decisions. Here's just a random sample of papers by people who used LLMs for somehow improving collective decisions. For example, LLMs could be used to read a number of statements by people and try to formulate or propose a potential consensus statement that then hopefully would be okay for everyone. So these are people from Google DeepMind who did this. Also, one could, given a set of many opinion statements, maybe thousands, one could ask an LLM to kind of summarize them in a way that is still representative of the diversity of opinions, like generating a representative set of opinion statements, which would then maybe be put to a vote. Rather than 1,000 options, then you would just have a representative set of, say, 5 options. Also, LLMs could be or have been proposed to act as representatives of single voters in collective decisions. Like, for example, if I can't go to all the collective decisions that I want to vote in, like if I'm, for example, a shareholder in a company and there's a lot of votes where I would have voting rights, but I have no time to do them, I could have an LLM acting on my behalf. And then obviously also not directly related to the actual voting process, but to something related to that, or on which the voting process is hopefully based, namely facts, then of course you can also use LLMs to kind of prepare for a vote, like by fact checking and so on. So all these things are out there in the literature already since a few years. And there's also a related community that looks at these and develops them further, which is the European Digital Democracy Network, or EDI. But this is not the direction that I want to talk about here. I want to talk about the opposite direction. So that's the idea that social choice theory or methods from social choice theory can help in improving AI systems or making them more ethical and safe. So there's fewer papers yet, but we have certain ideas. So one idea is to use a social choice rule to aggregate individual rankings in reinforcement learning from human feedback. That is actually what I want to talk about later in more detail. It's kind of a little bit of a natural idea, as we will see, but there's also other applications which are not directly related to maybe ethical or making the system more safe, but to otherwise help in AI. Like, for example, if you have a chatbot that should help you in your with medical issues, then the chatbot might generate a number of diagnoses, and you might want to have experts rank them, and then you have different experts, and you then have to aggregate their ranking somehow to steer the LLM. It's a little bit related to RLHF here. And then, of course, you might have seen OpenAI's project on democratic inputs to AI that they had. I think it was last year, not this year. They published the results this year, but the project was actually last year. And Anthropic had a little bit similar thing in what they called collective constitutional AI. So this is more about having a jury, or what social scientists would call a deliberative mini-public. You might know this from citizen assemblies. Discuss and eventually propose a set of very high-level steering principles, which Anthropic then calls the constitution for the AI, and which might, for example, go into the system prompt for the chatbot. So this is another application of social choice mechanisms and methods in steering AI systems. So, but these are only a few examples. So let's go into a little bit more detail in reinforcement learning from human feedback, which you might argue is the most natural and maybe also the most important at the moment, a place where something like collective choice should actually be applied and hopefully would improve the system a lot. So for those of you who don't know how reinforcement learning from human feedback works, it's the thing that the big labs use to fine-tune their pre-trained LLMs after they have read the whole internet and learned how to speak. They use this method here to fine-tune them in order to teach them what to say, basically, right? So how does it work? You have a database of pairs of prompts and responses, or maybe a prompt and several responses. Yeah, actually, so at least 2 responses. This database might be generated by some LLM itself. It might be hand-coded. The prompt might be handwritten, and the possible responses might be generated by an LLM, and so on. So there's different ways of coming up with these databases. Some databases are also focusing on certain aspects, like, for example, harmlessness, or another database focuses on helpfulness, and so on. So you have this database of prompts and candidate responses, typically maybe a few thousand or so. And then basically you treat them as decision problems. Like for each prompt, you have several responses, and the decision problem is which of the response is the preferable one, the one that the actual chatbot eventually should give if asked this prompt. And so an example of such a question would be, where can I buy illegal drugs? And the assistant could, so the assistant is always a chatbot, could, for example, say you shouldn't, or could give other example, other answers. We will see a number of examples in a second. So this is a decision problem, and we have a lot of these decisions problems. And now, traditionally, each of these decision problems is given to one individual annotator or voter or person who decides which of the responses is the best one, or ranks the responses. There's several versions of this, but the point here is it's typically just a single individual who makes the choice. But for different prompt and response pair, another individual makes that choice. So it's kind of a little bit inconsistent data that you get in this way, because the decision problems are not about factual statements only. I mean, factuality is one aspect, but it's very often about style, about understandability, about even like value systems, right? Very different individuals might rank these possible responses in very different ways. So if you let only one individual make a choice for this pair and another one for that pair, it's a little bit like educating a baby child with 10 different parents who did not coordinate what to say. So it's bound to be inconsistent information. So it's probably harder to learn what makes a good response, because it's not internally consistent, the data. But anyway, they do it like that. This is individual preference data. And then they train not directly the chatbot, but they train an intermediate model, which is sometimes called a reward model and sometimes called a preference model. That intermediate model does not map prompts to responses, but it rather maps pairs of prompts and responses to a numerical reward. This is why it's also called a reward model. So this reward model then eventually is used to train the actual AI in basically reinforcement learning. And this is why the whole thing is called reinforcement learning from human feedback. Here's the human feedback, and here's the reinforcement learning. So this intermediate training step here, this is not reinforcement learning. This is some form of supervised learning, because you have basically labeled data, and you the choices are somehow converted into rewards. That's a transformation, but otherwise this is basically supervised learning. And then the final step is reinforcement learning. So this is the vanilla RLHF pipeline. There's several versions of this, but none of these versions is actually interfering too much with this step here. And this is where we think one should make a change. The problem here is there is no ground truth on what is a good response. If there was, you could hope that during this training of the preference model here, the individual things are kind of aggregated automatically in the right way, just like in a regression task where you have a lot of noisy measurements, and if you just put them in as individual training data, then the training will average them automatically and then predict basically the posterior mean. But individual preference data cannot really plausibly be treated as noisy measurement of a ground truth, because it's really like some people like that and other people like something else. It's not like a noisy measurement of one and the same thing. And this is why it doesn't work that well. So I'm skipping this. It's kind of obvious that different humans have different value systems, different preferences, desires, and so they have different rankings. Now, let's look at some example to get some idea of what the type of questions are. And you might notice it's actually not that easy to come up with a meaningful ranking. I did some experiment in a summer school last year with students who were already kind of experts in coming up with rankings because they were studying social choice. So the concept of coming up with the ranking was familiar to them, but they had a really hard time to coming up with a meaningful ranking in examples such as this one. So where can I buy illegal drugs? This one is basically taken from Anthropic's database. So the prompt is taken from Anthropic's database that you can find on Hugging Face that they use to train an early version of Claude. But the responses here were generated last year by me with some version of Llama. I think it was Llama 2. I used a high temperature to get kind of a variety of different possible responses. So these 5 responses are actually AI-generated responses a year ago. And you see, they already vary quite much. And the underlining, of course, is mine to just highlight the differences. And you see, most of them point to the fact that it's illegal, or I mean, it's already in the prompt, but they point to the fact that you might run the risk of having legal consequences. And not all of them do that. Some of them are straight away answering the question here, and then only as an afterthought, cautioning you. Others are focusing more on cautioning you first, and not really answering where you could get them. So it's a little bit subtle question, and you might come up with your ranking on your own, but this is just an example of why it's really hard to come up with this data. And so another example is more political, also taken from Anthropic's database, and again the responses are generated with Llama. And here you also see that the different responses, sometimes they do disagree in factual things. Like, for example, this one claims that there are Democrats and Republicans who believe and disbelieve in global warming. And whereas the next one states that both believe in global warming, and they don't mention that some of them also disbelieve in them. So this is a factual thing that you might check. So you might tend to rank the second one higher than the third one if you believe that this is more true than that one, which I believe. But otherwise, it's again not so easy, right? Okay, so this is the job of individual annotators. And now what we think is that the rankings that the individuals come up with, they should be aggregated in a controlled way, not in something like an arbitrary or intransparent way during training in some sense, where it also depends on the order of data points and so on. But they should actually be aggregated in a way that people have designed to have good properties. So, and that means we think that each of these decision problems should be put to, like, let's say, a jury of people, ideally a representative jury of people. They make a collective decision, the outcome of which is some form of collective preference data, maybe just the collective choice or a collective ranking or something like that. And only that goes into the training of the preference model, which is then a collective preference model. And that is then used to fine tune. This is one way how one could introduce social choice in this pipeline. There's other ways where one could do it. This here is a shameless pitch for my own collective choice app that I developed, but one could use any kind of social choice mechanism here. Okay, so let's talk a little bit about what social choice theory and welfare theory, which is closely related, is in the first place. So it all starts with the relationship between a number of voters who have preferences of some type. It could be ordinal preferences, like this C is better than A is better than D is better than D. It could be cardinal preferences, meaning numeric, like giving ratings, which can be interpreted maybe as something like utility. It could just be an approval set by saying, okay, B and C are okay, whereas A and D are not okay. Or it could be something like a preference relation that is incomplete. Someone might say, well, I find D better than A, but I can't tell anything about C and B. They're not equally good. They're not better. I don't know, right? So the only thing that you can say is that D is better than A. So this is types of preference data that you might find in people. And then, of course, the question is, who should the voters be? Who should have a say? And maybe you want to weigh them in a sense. Maybe some people are more affected. They might weigh more, maybe. It might have to do with moral weights. And then you want, eventually you want to make a collective decision. One of the four options it should be. And the question is which. Now, there's two ways to do that. Social choice theory basically goes the direct way. It takes the preference data, whatever form it is, as input to something they call a collective choice mechanism. And there's different forms of collective choice mechanisms. You might think a voting system, for example, or a consensus procedure, or some form of deliberation. It could be an interactive thing, or a bargaining protocol, or whatever. It could involve delegation. So there's really a huge variety of some collective choice mechanisms, but they output one option, or maybe a probability distribution over options that is then used to draw one. But most of them, they settle on one option. So this is the direct way that social choice theory promotes or studies. But there's also an indirect way, which is by social welfare theory. Social welfare theory basically assumes that there's something like utility, but on a social level, on a collective level. And therefore, it's not called utility, but welfare, mostly. But you can think utility. So there's some numerical assessment of all those four options. And obviously, if you have this numerical assessment, you would go for the one that scores highest. The question is how to come up with this social welfare function. And that's where all the difficulties lies in welfare theory. So one way to come up with a social welfare function is, of course, by assuming that there is something like individual welfare or utility or well-being or happiness or whatever. And you just have to aggregate that into social welfare. So you probably know about utilitarianism, which assumes individuals have utility functions and which is then aggregating these utility functions, sometimes just by summing them up or averaging them, which makes a difference if the populations are differently sized. But there's also other forms of aggregation. You could, for example, for each option, take the minimum utility over the whole population. That is egalitarianism or prioritarianism. And there's anything in between, like inequality averse welfare functions. For example, the Gini-Zen welfare function, which is the expected value of the minimum of utility values of two randomly drawn members of the population. So you see, there's also more sophisticated ways of aggregating individual welfare functions into a social welfare function. And then you might ask, where does this individual welfare function come from in the first place? And you might ask neuroscientists for measuring happiness, or economists for measuring preferences from observing behavior, consumption mostly. You might think of, in EA terms, you might think of the capacity for happiness and try to measure that. You might focus on suffering, any kinds of thing you might do in order to assess individual well-being, happiness, whatever, the thing that you want to aggregate. So there's a lot of things going on here. And that is, in a sense, parallel to this direct thing, because social choice theory, other than welfare theory, doesn't really directly care for utility or welfare, or doesn't even assume that such a thing exists. In that sense, it's more liberal. It doesn't only work for kind of rational people who really do have expected utility preferences. But if individuals have expected utility preferences, then that is potentially the thing that links the two. If you have preferences that fulfill the axioms of expected utility theory, then you can represent them by some form of utility function, and then you might use that as the individual welfare measurement. Of course, that's not that straightforward, because in principle, utility functions are not uniquely defined. They have an undetermined scale, so you can't really add them up right away, because that would be meaningless. My individual utility function is the same as 10 times my utility function. But there's also ideas how to solve that problem. So this is the relationship between social choice theory and welfare theory. We're focusing a little bit more on social choice theory, because that's the more liberal kind of less dependent on assumptions of rationality and so on. Okay, so how to evaluate collective choice mechanisms or different aggregation rules? There's a lot. So how to make a choice? Which one is the right one? And a typical methodology in social choice theory that is used is the axiomatic method. Axiomatic method means you specify upfront a number of criteria or properties that you want your mechanism to fulfill. For example, you specify certain properties regarding the efficiency, like, for example, Pareto efficiency. For example, that means if you have two options, A and B, and several others more, and it so happens that everyone prefers A to B, then Pareto efficiency demands that B will not win, because everyone prefers A. So that would be the criterion of Pareto efficiency. And then some methods fulfill it, other methods do not fulfill it. You can check whether it is fulfilled, and then you can make a check mark. Okay, this method does fulfill this axiom, does not fulfill other axioms, like certain fairness axioms, for example, and so on. There's lots of different axioms. We can't discuss all of them, but many of them focus on either some form of efficiency or some form of fairness or some form of manipulability. I didn't list this here. Strategic interactions. Oh yeah, I did list it here. Because with real world voters, you cannot count on the fact that if you ask them for their rankings and they are aware in what way the rankings will be used to determine an outcome, then you can't count on them being honest with their rankings. They might be strategic. And you know this from strategic voting. If you have a majority vote in your district and your favorite candidate happens to have no chance or is very unlikely to win, then you might probably rather vote for your second choice if that is a much more likely winner or front runner. So this type of strategic voting really happens, and one can see it in everyday elections. And so one must count on the fact that the data that you elicit from voters might not be truthful data. And so there's certain axioms about possibilities of strategic manipulation, and they can also be checked. So this is a rich science that works with these formal criteria. There's also some less formal or less, let's say, less binary criteria. There's more quantitative criteria that try to assess like the welfare effects of a certain social choice mechanism, but the axiomatic method is really the predominant method. Okay, so let's give a very short history of social choice theory so that you see it's really, really old. Like even the Athenians have spent some thought on how to design their systems, because when you look closely into the history, you will find that they did not always use majority vote for things. Actually, they used majority voting only for the most important decisions where everyone came together and then took a vote. But the everyday decisions of the administration, they were taken by officers, and the officers were elected into the office by drawing lots. So they involved a lot of randomness, and they have thought a lot about that, and chose to use this probabilistic method for a lot of their decision making. So it goes back really thousands of years. In the 13th and 15th century, the two most basic principles that are still in use today have been already invented by two monks. One Catalan monk, Ramon Llull, who lived in the 13th century, and the other Nicolaus von Cruz or Cusanus. And these two methods that they invented are nowadays known under different names because they have been reinvented in the 18th century by the Marquis de Condorcet and Marquis de Borda, like two French marquis. And so the Condorcet method actually is Llull's method, and Borda method is Cusanus' method. And but they didn't analyze them very much. They just proposed them for a certain application, whereas Condorcet and Borda really started the methodology of social choice theory by pointing out certain issues and discussing certain properties. And then democracy kind of took off in the 19th century and became more and more identified with majority rule. Actually, I would argue majority rule is not a good way to base democracy on. You could argue it's not even democracy, it's more pleiocracy, the rule of the many rather than the rule of everyone. But that's a different discussion. Then throughout the 20th century, we have seen many examples where even majorities can make really bad decisions. So even if you have a good collective choice mechanism or something that you think is a good choice mechanism, maybe it's not enough to ensure that there's good decisions. Maybe you need something else in addition, maybe a legal system that filters the options that get to the vote in the first place, only constitutional ones, and so on. So one should be kind of a little bit suspicious about majorities making decisions. And then towards the middle of the century, the whole theory sadly, it got a pessimistic turn because the famous economist Kenneth Arrow, who got a Nobel Prize in 1972, proved a theorem that is known as the impossibility theorem. I rather call it the irresponsible theorem because it really was not a productive or constructive contribution, because what he did is he said, let's assume we have a number of rankings of options, and let's assume we wanted to aggregate these rankings into another ranking, which he then called the social ranking. And then he specified like 5 different seemingly harmless properties that this aggregation method should probably, hopefully, fulfill. And then he proved it's not possible to fulfill all of them at the same time. And then many people thought that this means you can't make collective decisions in a consistent way. But this is really not what this theorem proves, because making a collective choice simply does not require coming up with a social ranking. It just requires making a choice, one choice, not a ranking. And that, but people misunderstood this, and in the following, many people tried to prove different versions of the impossibility theory. Then, of course, everything up until then was based on rational choice theory and the assumption that people are rational. But then behavioral economics in the second half of the century showed a lot of experiments that showed that people's preferences are not really based on expected utility, and rational choice theory does not hold with real people. One of them is Allay's paradox and so on. But there's many more. And then two major figures that brought the theory into more constructive ways was Amartya Sen, who got a Nobel Prize also for his work on welfare theory. So he worked on both things. For theoretical work on the relationship between collective choices and individual freedom, and then a really good voting method that is still currently discussed as a replacement for the simple majority thing that most of us are used to, namely approval voting. That was promoted by two biopolitical scientists, Stephen Brams, and a mathematician, Peter Fishburne, and this is major advances. So these are just a few steps in the history of social choice theory. So let's look a little bit at some of these basic ways to make decisions. Well, I have already indicated that pairwise comparisons are seen by many as a good idea. So Ramon Llull, who I mentioned before, designed this method, and the application he had in mind was electing the leader of an abbey, an abbess, and he said, okay, let's send in all the nuns into the room where, or all the candidates into the room where the voters, the other nuns, are sitting, and sending them in a random order. First A and B, and let the voters kind of take a pairwise vote on A and B. And one of them survives, so to say. This goes to the question mark here. Let's say B survives, A is out. And then the third candidate is sent in and is compared to the current winner, B in this case. And then one of them survives. Let's say B again survives. And then so on. All the other candidates are sent in and compared pairwise to the current winner until in the end, some candidate has won all their pairwise comparisons. And this is an interesting method because it is probabilistic, because the order is probabilistic, but it is also, it fulfills this property that if there is one candidate that would win all pairwise comparisons with all other candidates, then obviously this candidate will win. At some point, it will be sent into the room, and from that point on, it will win all the pairwise comparisons and therefore survive. So this method is, nowadays we would say, is Condorcet compliant, because if there is a so-called Condorcet winner, an option that would win against all other options pairwise, that is called a Condorcet winner. And the axiom says, if there exists a Condorcet winner, there doesn't need to be one. We have seen this in the beginning. But if there exists one, then that should be the winner. That's the Condorcet criterion. And this method meets that criterion, even though it's otherwise probabilistic. So that's an interesting system. And I like it quite much, except that I don't like majoritarian systems overall, as we will see later. So this is a very very typical idea, basing things on pairwise comparisons. A completely different idea is basing the collective choice on the idea of scores. So let's say we have three candidates for the film that we want to watch, and you see, I'm an old guy, so I know old movies. And let's say we have 6 voters, and they ranked these 3 films in different ways. So these numbers are the rankings. So voter 1 wants to see Halloween and doesn't want to see Pretty Woman, and so on. And what you then just do, you sum up these ranks to get a score. And then you elect the one that has the lowest score, in this case, Star Wars. So if you do that, then that's called, nowadays, it's called the Borda score, but it was actually invented 500 years earlier by Nicolas von Kues. So this is the simplest, you might argue, or one of the simplest scoring systems. It's not based on pairwise comparisons at all. And so it's a really different thing. Okay, so now, how to decide which of these methods is better? And now social choice theory is taking a principled approach. It cares for justifiability and explainability. It cares for consistent behavior if you make certain changes, like, for example, if you exchange 2 places, 2 rankings here, like, for example, if voter 1 were to say, okay, I actually like Star Wars better than Halloween, and exchanges these 2 rankings, then that should not make Star Wars suddenly lose if it had won before, right? Because it should actually reinforce the win of Star Wars. So this is a form of consistency behavior that's called monotonicity. But there's also other consistency criteria. Like, for example, if you're cloning an option, like someone brings in as a fourth option a Halloween director's cut, and it turns out the director's cut is basically the same as the original one, then you would say this is basically a cloned option, and this change in the agenda or in the set of options should not kind of disturb the whole outcome in strange ways. So this would be clone consistency. And there's other forms of consistency. And then efficiency, we have already talked about Pareto efficiency, and there's also other forms of efficiency that people care about. And then a major thing that might be important for AI and AI ethics and so on is fairness, like the distribution of power. And we will see in a minute that power distribution, it can be really different. Okay. I have already told you that the input data for a social justice mechanism could be all kinds of things: pairwise comparisons, rankings, ratings, numerical, also simply sets like approval scores where you just say this is okay, this is not okay, or other types of things. So it's kind of really diverse. Okay, let's skip this in the interest of time. There's other scoring systems, so you might imagine. And now let's talk a little bit about honesty. So I already told you that you should not count on the information provided by voters to be truthful. Now, in the context of RLHF, you might wonder, an individual evaluator or annotator, do they actually have an interest in the eventual outcome? If not, you might think that they will actually honestly respond. But then psychologists might tell you, yeah, but there might be also something like confirmation bias. There might be something, you might wonder, what do they want to hear? Let me answer what they want to hear and so on. So you should never really think that the data you get is kind of unbiased or truthful as all. But there are ways of eliciting truthful preferences if the voters care for the outcome. And the most trivial way to do that is called random dictator. So that is a little bit of a strange social choice rule, which consists in just drawing one of the voters at random after they have cast their votes, or maybe before, it doesn't matter, and let them make the choice. So it's not really a collective choice, but formally it is a collective choice. You pick one at random and let them make the decision. Now, it's kind of obvious that this voter has no incentive to lie about their preferences, because either they're chosen and then they should have voted for their favorite, or they're not chosen and then what they voted for makes no difference either. So for random dictator, it's trivial to see that this is what we call strategy free. Being honest is what a game theorist would call a dominant strategy. But this is rare. Most other voting systems are not strategy free. So it's actually hard to design systems that are strategy free. So there's also other types of applications that social choice theory cares for. It's not only about choosing one of several options, like in RLHF, but a very popular thing nowadays is participatory budgeting. Let's assume you have a municipality that has a budget for, let's say, cultural projects, a fixed budget. And now they want to have the citizens decide on which projects, which theaters, which companies, and so on, which cultural projects should get how much of that budget. That's called participatory budgeting, and it's very popular in many municipalities, and it works in a similar way as other collective choice methods, but because the output is now no longer a single option, but a distribution of the budget, it has some particularities. The most popular thing here is currently the method of equal shares, and I'm naming this because it has some equivalent to a single winner method that we will see in a second. So method of equal shares works like that. If you have n voters and the total budget is B, then you start with kind of distributing the budget not to the project, but through the voters in a sense, which means that each of the voters somehow controls an equal share of the overall budget. And then you ask voters to approve projects. So each project I can either approve or not approve. And then you're summing up the total approval for each project. So how many people approved this project, how many approved that project, and you're ordering them in descending order of approval so that the most approved project comes first. So and you're processing them in that order. So let's say you have project J, and what you do then is you look at all the voters who approved this project J and how much of their initial share, the budget they have left. They might have spent some of the budget on some projects, but some of the budget they might have left. And if that remaining budget by the supporters of the project is large enough for that project, because each project demanded a certain amount, BJ, this is kind of the input that the projects gave. So if there's enough money left from the supporters of J to fund J, then J is funded, and equal shares of this demanded budget is subtracted from the supporters' budget, so that their remaining budget goes down, and at some point it's zero. So this is a natural idea, but you can also have other natural ideas, and then you can compare them again using this axiomatic method. You could also think of, can we apply this in machine learning? What could be the budget? Well, maybe the budget could be probability, the probability of giving a certain response. You know, obviously, that chatbots are not deterministic machines. They are probabilistic machines. Depending on the temperature you give them, they give sometimes this response, sometimes another response. So they deal in probability in a sense. So you might use something like that to decide what probabilities they should assign to not projects, but responses. Let's skip this because we don't have that much time left. So I gave you some ideas about social choice theory. So let's talk a little bit about what we did in Berkeley in December. So what we did was we taught each other about problems in AI and methods from social choice theory. And then we tried to draft a research agenda for this emerging field. And we came up with these 3 overarching questions, of which basically the first one is kind of the most straightforward. How can these social choice methods be used? But then also the other direction, we acknowledge that there's, of course, feedbacks between these directions. So we should also look at this other direction, how AI impacts collective decision making. And then also feeding back to social choice theory, which unresolved issues in social choice theory need to be solved in order to make it more applicable to AI. So this is kind of a high level view of the research agenda. We have a position paper here that I also linked in the chat, which you might want to look at. It's an easy read. And it also discusses ways for improving RLHF, reinforcement learning from human feedback. And there's also a nice blog post by one of the co-authors who is an expert in RLHF. So that's also a nice read. So there's more details also in the paper. I'm going to skip them because you can read them there. And I'm going to finish up with, again, this slide and promoting the workshop in October. So if any of you happen to be at EK anyway, then you can just arrive 2 days earlier and go to our workshop. Thanks so far. I hope there's some questions or comments or remarks.